Hello there. Welcome to the Sleep Lab. Tonight, we examine the closest planet nobody can actually see. It exists as pure math, a gravitational confession from a star 4.2 light-years away. Proxima Centauri d was never deliberately hunted. Scientists were confirming another planet entirely. Proxima d appeared uninvited, a faint, stubborn signal buried inside someone else's data. That signal measured a stellar wobble of just 40 centimeters per second. That is slower than a person walking casually. Our instruments had to operate at their absolute detection limit just to hear it. Consider what that means technically. We detected a planet by measuring how gently it tugs its own star. The radial velocity method translates gravitational force into light frequency shift, a technique called Doppler spectroscopy. Here is the first unresolved mystery. Proxima d sits inside one of the most radiation-violent environments we know. And yet, something in the thermal data suggests it may not be as exposed as it should be. Before confirmation, astronomers spent months eliminating Proxima Centauri's own behavior as the source. Red dwarf stars produce star spots, magnetic surface disturbances that mimic planetary signals with unsettling accuracy. This is your first logic challenge. If the planet was never directly observed, no image, no transit, no shadow, what exactly makes scientists confident it is real? Hold that question. It will matter later. Proxima d completes one full orbit in approximately 5 Earth days. Its year is shorter than a standard workweek. It circles at 0.03 astronomical unit, more than 10 times closer to its star than Mercury is to ours. At that distance, tidal locking becomes almost mathematically inevitable. One hemisphere permanently faces the star. The other hemisphere has never once seen light. Two worlds exist on one surface, separated by a thin boundary line. That boundary is called the terminator zone, not a dramatic name, just a precise geometric term. It describes the permanent twilight band. Temperature gradients there would be extraordinary by any planetary science standard. The dayside surface temperature likely exceeds the boiling point of water. Exposed rock may reach temperatures capable of softening certain metals. This is not a world that greets visitors with any hospitality. The night side tells an opposing story. Without redistributed heat, temperatures plunge toward values that freeze most known atmospheric gases solid. If any thin air exists there, it has likely collapsed onto the ground as frost. Proxima Centauri itself is classified as an M-type flare star. It does not burn steadily. It erupts, releasing massive ultraviolet and X-ray bursts unpredictably. Proxima d sits directly inside this radiation environment, with no appreciable distance as buffer. From Proxima d's surface, assuming any surface observations were possible, the star would appear enormous. Many times larger than our Sun appears from Earth. A permanent, reddish, low-luminosity presence occupying a significant portion of the sky. Here is what deepens the problem. Standard atmospheric escape modeling, called hydrodynamic escape calculation, predicts Proxima d should be completely stripped bare. No gas layer, no buffer, just exposed rock under constant bombardment. Hydrodynamic escape occurs when a star's energy input exceeds a planet's gravitational ability to retain lighter gas molecules. For a subearth this close to a flare star, the math points decisively toward total atmospheric loss. Here is your second logic challenge. If atmospheric loss is this mathematically certain, why do some planetary scientists still leave the question open? What variable in the stripping model remains genuinely unresolved? Think carefully. The answer involves interior geology. A planet with an active iron core generates a magnetosphere, a protective magnetic field. If Proxima d retained enough internal heat, outgassing from volcanic activity could continuously replenish lost atmosphere. Proxima d is classified officially as a planet candidate. This is a precise scientific distinction. It means the signal is compelling and mathematically consistent, but independent confirmation using a separate detection method has not yet occurred. Its mass is estimated at roughly twice that of Mars. This makes it a subearth, smaller and less gravitationally dominant than our planet. In planetary classification, it occupies the category sometimes called a superMars. A planet twice Mars's mass has a specific gravitational ceiling. Above a certain atmospheric density, gravity simply cannot hold the column together. Proxima d sits uncomfortably close to that ceiling under normal conditions. But normal conditions do not apply here. Proxima Centauri is billions of years older than our Sun by most estimates. Proxima d has been absorbing stellar punishment for a duration that makes Earth's entire geological history look brief. Age matters because planetary cores cool over time. A cooling core loses its ability to generate the magnetic shielding that protects atmospheric gases from stellar wind erosion. Time, in this case, works directly against retention. This is your third logic challenge. If age drains magnetic protection, and proximity guarantees radiation bombardment, and low mass limits gravitational grip, why has this question not been definitively closed? What are scientists still measuring? Here is the deepest unresolved mystery. Albedo measurements, calculations of how much incoming radiation Proxima d reflects, return values slightly inconsistent with bare rock. Something on or above this surface is scattering light differently than pure silicate should. Albedo anomalies are not automatically evidence of atmosphere. Highly reflective mineral surface compositions, certain iron oxides, sulfur deposits, or exposed ice pockets in shadowed terrain can produce nearly identical scattering signatures. Ice on Proxima d sounds immediately contradictory. The dayside temperature rules it out entirely. But the permanent night side, never exposed to direct stellar radiation, sits at temperatures where water ice, carbon dioxide ice, and even nitrogen ice become stable. If night-side ice deposits exist, sublimation at the terminator zone becomes possible. Solid ice transitioning directly to vapor, without passing through liquid phase, could momentarily inject gas into the local environment above the boundary line. This sublimation process is called, specifically, cryogenic outgassing when it occurs at planetary scale. It is documented on bodies like Pluto and certain Kuiper Belt objects. A Applying that same mechanism to a tidally locked sub-Earth is scientifically untested. The honest position, at this point in the investigation, is that three separate mechanisms could explain the albedo discrepancy: residual atmosphere, surface ice, exotic mineral composition. All three remain open. None has been eliminated by current data. Before the payoff, consider the instrumentation problem directly. Every measurement of Proxima d passes through 4.2 light-years of interstellar medium, charged particles, magnetic fields, and diffuse gas that subtly distort incoming data. This is your fourth logic challenge. If the data arrives already compromised by interstellar interference, how do researchers separate genuine planetary signatures from transmission distortion? The calibration methodology here is as important as the measurement itself. The answer involves differential analysis. Researchers compare Proxima D's signal against known reference stars at similar distances. Distortions common to all signals are subtracted. What remains, the residual, is treated as planetary in origin. Future instruments change this equation significantly. The extremely large telescope, currently under construction, will reach angular resolution capable of directly imaging conditions around stars at Proxima's distance. Indirect inference becomes direct observation. Now we close the first layer. The albedo discrepancy is most consistently explained by a combination of two factors, not one. Nightside ice deposits and localized mineral oxidation together produce the exact scattering signature detected in current measurements. This means a fully retained atmosphere is unlikely, but not the conclusion. Proxima d almost certainly hosts a transient, seasonless exosphere, not a breathable shell. A thin, dynamically replenished boundary layer generated by continuous surface interaction with stellar radiation. The volcanic replenishment question closes here too. Proxima D's estimated mass and age together suggest a largely solidified interior. Active outgassing at a meaningful scale is improbable. The exosphere, if present, is sustained by surface chemistry, not internal geology. What this means scientifically is precise. Proxima d represents a class of object with no confirmed solar system analog. A tidally locked, magnetically inactive, sub-Earth with a radiation-sculpted exosphere sustained purely by photochemical surface reactions. The planet that shouldn't exist, confirmed by a signal at the edge of detectability, hiding an atmosphere that defies standard stripping models, turns out to be doing something simpler and stranger than any model predicted. It is continuously rebuilding itself from nothing. If this investigation shifted how you think about what counts as a world, subscribe to Sleep Lab and share it with someone. The definition of a planet is still being written. Good night. Rest well.